Good evening. Welcome to the QCIS channel. On this channel, you get a daily dose of science, technology, engineering, and math. My name is Leon Jones, and I got another good topic for you. I'm going to talk about a traverse computation. Now, as I talked about last night, when we deal with simple traverses, you had the distances, you had the elevations. Wanted to make sure that you actually closed everything. That are certain concepts that you have to use. Now, that one just involved elevations and distances. Now, this one is going to get into a little bit more depth. I'm going to get into what if there aren't any bearings? How do you find a bearing? Well, I'm going to share my screen and we're going to get into some of that. Okay. As we talked about last night, we're using what we call the Bowditch method. Now, if you have the book, that's Ghilani's book, Introduction to Geomatics, Elementary Surveying, chapters 10.1 to 10.8 is where this information is coming from. Now, we're making traverse adjustments. And what we're going to be doing is locating blunders in a traverse. Now, here in the PowerPoint, you see that the traverse, which is a polygon, you have a missed closure. In other words, it doesn't close. Again, when we're dealing with angles and polygons, you have to use the formula n plus 2 times 180 if you're dealing with external angles, and minus 2 times 180 when you're dealing with external angles. Each of your polygons should come out with different degrees. If you have a hexagon, you should have 1080 degrees. If you have a square, a rectangle, 360 degrees. Now, here's some of the polygons. Now, what we do, you want to make sure that you get everything into proper organizations. So there's steps. You're going to adjust angles or directions to fix geometric conditions. And you have to determine what we call bearings or azimuths of traverse lines. And you get into calculating departures and latitudes. And your departures and latitudes are your northings and eastings. Then you deal with computing rectangular coordinates. And then you calculate lengths and azimuths. Now, here's what you do. And this is one thing that I would hinge on. It's organizing your data. If you don't know where you are, your data is not going to be accurate. So before we start any computation, especially complex computation, organize data. Now, look at what you have on the screen here. You have to identify the traverse angles and distances. So what happens is we're assigned a coordinate of 5,000, 1,000. Okay, now in this one, we're given a known azimuth of 126, 55, 17, and we're given a five-sided polygon. So what we're supposed to do is assign an azimuth from the first occupied point to a foresight. Now, when we deal with surveying, we set up on a point, and when we look to the point in front of us, that's the foresight. When we turn an angle, which is generally 180 degrees, that's the back sight. Now, this can be approximated to the nearest degree. Here's where the formulas come into play. Determine angular closure error. Interior angles equal n minus 2 times 180. Exterior angles equal n plus 2 times 180. Now, here's the polygon. Here's all the information you're given. You have your known azimuth. You actually have your interior angles here. Now, what's going to happen? You're going to add all of your interior angles that are measured. Remember, these are your angles that are measured when you go out there with the instrument and you turn the angles. Now, when you have a 5-sided polygon, if you use for internal angles this formula right here, n minus 2 times 180, you're supposed to end up with 540 degrees. How did I get that? I took 5 sides minus 3, which a correction, 5 sides minus 2, which gave me 3 times 180, which gives me 540 degrees. Now, when I add each angle up, I come up with 11 seconds greater than 540. So what does that mean? Well, there is an error of 11 seconds. Now, since I am greater than 540 degrees, it's going to trigger in my head here, I'm going to have to subtract the seconds, 11 seconds. So how do I do that? Well, I'm going to balance everything out. Now, this is where we get into balancing angles. Now, there are 2 methods. Now, here's what we do. Average of error applied to each angle. A, you divide the number of angles. Add or subtract this amount to each angle. So basically what you do is you have 5 points right here. 1, 2, 3, 4, 5. So you take the time or your error and you divide it by the number of points. So they took 11 seconds and divided it by 5 and they got 2.2 seconds. Or you make larger corrections to angles where poor conditions existed. I like using the latter one because it's much easier. So what we do, we have a chart, error adjustment. So we already have 2.2 seconds that we're going to be distributing basically to each angle. So looking at the chart, because we put everything in a chart, the error correction needs to compound each time it's applied to the next successive angle to account for the previous angle adjustment. And that should successfully total the error. Also, column B, the adjustment should be rounded to the correct significant digits. Then you check on the differences. The total must equal the initial total error. And then you can go ahead and take the successful difference and apply it to its associate angle to obtain an adjusted angle. Again, the error in this problem was plus 11 seconds. So what does that mean? We have to subtract 11 seconds. So here's what we have. In the first column of the table, love to set everything up in a table. It's organized. We have our points. Then we have our measured internal angle. And we add our internal angles up. And then we have multiples of the average correction. Now, how did I get all of these numbers right here? Well, when we divided 11 seconds by 5 points, we got 2.2 seconds. So when we took multiples of 2.2 for each point, we basically doubled and tripled it. And here's why you do that, because you want your multiples of your average correction to equal your error. For instance, we have 2.2. You double 2.2, you get 4.4. You add 2.2 again, you get 6.6, then 8.8, and then 11. Now, when you go ahead to the next column, what you do, you basically round everything up to the nearest 1 second. So here's what they did. They rounded 2.2 down to 2 seconds, 4.4 down to 4 seconds, 6.6 down, well, they rounded it up to 7 seconds, They rounded 8.8 up to 9 seconds, and of course, 11 seconds. So then we have our successive differences. Now, how do we get that? Okay, here's the way we do it. Well, when we go from 2 to 2, that's going to be 0. But when we go from 2 to 4, that's going to be 2. When we go from 4 to 7, that's going to be 3. When we go from 7 to 9, that's going to be 2 seconds. And then when we go from 9 to 11, 2 seconds. Now, what did we do? Successive differences. We basically distributed all of the seconds equally. So now, when you look in your last column here, you take your measured angle and minus your successful difference, and then you get the adjusted angle. So in other words, we have an angle of 100 degrees, 45 minutes, and 37 seconds. We subtract 2, we have 100 degrees, 45 minutes, 35 seconds. The same goes for the next angle. So we're basically subtracting 2 seconds from 4 out of 5 of the angles. The only one that we're subtracting 3 from is the measured angle of 17 degrees, 12 minutes, and 59 seconds. And we get 17 degrees, 12 minutes, 56 seconds. Now, when we add all of our adjusted angles up, we have closed the traverse based on our adjusted angles. Now, the next thing we do, we have computation of preliminary azimuths. So we already had our first azimuth given to us at 126, 55, 17. So basically, are you going to go clockwise or counterclockwise? And it looks like in this direction, you have 126, 55, 17. So they're going to be adding 180. So they're going to be going clockwise. So when you add 180, then you, from AB, what you're doing is the 126, 55, 17 is your foresight azimuth. You're going to add 180, you're going to get your back azimuth. And then what you're going to do from there, you're going to take your interior angle, which is adjusted, and you're going to add it to your back azimuth. And you're going to continue to do that all the way down for each point. Now, you do that because the beginning angle, 126, 55, 17, that's your azimuth, correction, that's your azimuth, should equal your ending azimuth. So in other words, if you start at point AB, you should end up at point AB, like here. They're giving your azimuth of 126, 55, 17, you add 180, this is your back azimuth. Then from your back azimuth, you're going to add your internal angle of point B. Then you're going to get 531 or 538, 18, 58, subtract 360. And then you're going to get 178, 18, 58, subtract 180. This is going to give you your back azimuth of CB. You're going to add your internal angle, 17, 12, 56. You're going to come up with your azimuth, 375, 31, 54, subtract 180. Then you're going to get 195, 31, 54. Then you're going to add your internal angle. You're going to get your back at, you're going to get your azimuth at the next point, subtract 180. So basically, you're either going to add 180, subtract 180, and in this particular problem, you're going to add your internal angles. And generally, we're going clockwise. And then the beginning and the ending bearing should check perfectly. Now, something else you need to know. Now that we have all the angles, let's talk about the departure and eastings and latitude and northings. So basically what you're really doing is you're taking an angle and you're utilizing trig, sine and cosine. So How do I get all these departures and latitudes? Well, I'm going to take the cosine for the departure, the cosine of 126.55.17, and I'm going to multiply it by the length, and then I'm going to come up with my departure. Correction, I'm going to take the sine. When you do departures, you use sine. When you do latitudes, you use cosines. Let me repeat that again. When you do departures, you use sine. When you do latitudes, you use northings. Now, again, what I'm going to do is take the sine of the azimuth times the distance to get my departure, and it's usually in eastings. Now, what if I come up with a negative number? Well, your positive numbers are northings and eastings, and your negative numbers are westings and southings. You don't see westings and southings on this chart, but that's generally what they are because we're using what we call the compass rule. The directions are relative. They're not true. They're all relative. When you're traveling north or south or east or west on any highway, you're not going true north. Always remember that. So let me continue. So once we use this formula, we get all this information here, then we're going to total up our lengths, and then we're going to total up our latitudes and departures. Then we're going to find out what our misclosure is. So we're using what we call the Bowditch method. That's the most common method. And what this method does, it adjusts latitudes and departures in proportion to their lengths. Now, if you want to avoid rounding issues, carry extra decimal places through this procedure. I've had to do that sometimes. And always look at your formulas. Now, your departures, your total departures, misclosure times length of line equals your adjustment total traverse length. Same with your latitudes. Now, let's get into something before we actually look at the problem. The algebraic signs of corrections are opposite of those of the respective misclosures. So let me explain that to you. If I added up all my latitudes and departures and they were positive, well, the error I'm going to subtract, it's going to be negative. I'm going to be subtracting. I'm going to be subtracting the error. Now, if I had all negative for my latitudes and departures, then I'm going to be adding. So you take the opposite signs. I'm going to show you how that works in one moment here. All right. Now, here's what they did. They've added all the lengths. They've totaled up all of your northings. That's your departure, your eastings, that's your departures, and that's your latitudes. Now, what you have to do is you need to find out what your linear position is. So you're going to take the square root of your northings squared plus your eastings squared, and then you're going to have your relative position. Now, here's how you do this. Or what they've done, they took 0.026 and squared it, and then they have subtracted 0.077. They squared it, and then they took the square root and they came up with 0.081 feet. That's my linear position. Now, my relative position is they took 0.081 over 2466, which is the length. And then they came up with a relative position of 1 over 30,000. Now, how did they get that 1 over 30,000? Well, here's a trick. They took 1 and they divided it by 0.081, and then they multiplied it by 2466. So you already have your 1. So they're going to take this number and they're going to use the reciprocal. So in other words, the calculator here They use 0.081 divided by 2466. So they came up with 0.000328. And then they're going to multiply that by 2466. And you get, and you put a one over that 0.000328, and you come up with 304.87. So what you're really doing, you're taking one and you're dividing it by this fraction right here, and you come up with 30487.1. Now you already have your one, so you already have 30,487. So you're going to round down, you're going to call that roughly 30,000. That's how they came up with that. Now, when you go into your coordinates, you're going to be using a lot of these formulas here. You're going to take your sum of your latitudes and departures and divide it by your length, and then you're going to multiply it by the total length and then by the length of your point. And this is how they came up with 0.047. So in other words, they took 0.26, that is the sum of all your departures. They divided it by the total length of the polygon or the traverse, and then they multiplied it by each individual length from point to point. And this is how they came up with all of their information. Now, when you go through the chart, how do they get all these numbers? Well, you start off with coordinates 1,000, 10,000, 5,000, and you're just going to be adding and subtracting until you come up with you're back to where you started, and then you add all of your departures and latitudes up, because what you're doing, you're actually correcting your rectangular coordinates. Like up here, there's error, and so when we computed all the error, we use these formulas right here. This is how they came up with that negative 0.07 and that negative 0.20. And then the error is calculated. And then they take that error and they adjust it. 5.17.451 minus 0.007. It comes out to 517.444. So you're subtracting your error. And once you subtract everything, you go ahead and add and subtract from your coordinates until everything is zeroed out. Then you have your final lengths and azimuths as well. Now, what you do, you take your latitudes and departures for each point, you square them and take the square root, and that adjusts your length. Now, when you take your azimuths, you take the inverse tangent and you take your coordinates, you take your departure and divide it by your latitude, and you come up with your azimuth angle. And here's how you get your azimuth angle right here. And now you have your azimuths out here. You have to adjust those. You have your lengths adjusted. Now, when you go back, and these are your adjusted angles. Now you have your azimuths out here. Now, something you need to know. We had angles up here, your adjusted angles. Now your adjusted angles, particularly in this problem from step 5, are going to be a little different from your final adjusted angles. Because what we're doing here, we go right around. They got this 100 degrees, 45 minutes and 42 seconds because what you do, you subtract your back azimuth from your forward azimuth. Now here, you do the same thing. Because 306.55.23 is greater than 178.19.00, you add 360, and then you subtract, you get this number, 231.23.37. Here again, you're going to add 360, and you're going to come up with, you're going to subtract CB from, when you add 360, it's 375.31.54. You subtract 358.19.00 to get 1712.54. Now, you get these differences because the first angle, when we go back up to 5 and had our adjusted angle was 145.35. Now, our new or final adjusted angle was 145.42. So that's a difference of 7. And then you apply the same method to the computation for the rest of the points until you get 0. Now again, when we do side shots, they are not adjusted. Side shots are not adjusted. Now let me go see if I can pull up another one for you. All right. Here we go. Now, here's one that I actually did, so you'll know. Now, how did I come up with a known azimuth? Because I didn't even have an azimuth. Well, I was given a bit of information. I was given a coordinate, 16 and 17. Here are the coordinates I was given. So I took this formula, used the inverse tangent, gave me decimal degrees, and I came up with this first azimuth. That's now my known azimuth. And I went through the same procedures. Let's see if I can rotate this. All right. Came up with the same procedures. When I added everything up, I had some error. So what I had to do, I had to add it back in because I was 46 seconds shy of 360 degrees. So I did do that. And then I took 4 points. So you had minus 46. So I divided by 4 to get 11.5, added everything up. And here's my adjusted angle. And this is for a 4-sided traverse. Now, also, when you do these computations, you should have a drawing. You need to see where your information is going. Now, after I did all my calculations, here's what I came up with. Again, have a drawing. I want to rotate my drawing. Here's my drawing. This is now my drawing with the measured angles. And the measured angles were the ones I actually measured out in the field. Now, here's my drawing now with the adjusted angles. Okay, let me rotate it right. Okay, here's the same procedures as I computed departures and latitudes. Same thing they did. Except I came out with the opposite signs for my departures and latitudes. Came out with positive for my departures, negative for my latitudes, and look at the signs. Had to use negatives for my departures and positives for my latitudes. But the math is simple. So what did I do? I took, so you'll know what I did. I took 1 divided by 0.028 because I took the square root of 0.05, squared it, and I added 0.028, and that was the departure in latitude error. And I came up with a number times 1221.26. And that I had roughly 43,616. So what I did, because it was 43, my relative position, I said it was 1 in 40,000. So basically, again, with that relative position, what you do, you take 1, you divide it over your linear position, and then you multiply it by your total length. Because here, what I did, I added my total length up, like you saw in the PowerPoint. And then I have my balance, lengths, and azimuths, labeled all my points, and these are all adjusted azimuths. Again, always have a drawing. Let people know what you're doing and let them see the results. And here is one with all of the adjusted azimuths and lengths. And I did everything the same way. I took actually 215 minus 122. I got this number. I took 395, 5830. Got this number. Again, what I'm doing to get my adjusted angle, I'm actually taking a formula from my azimuths. I'm taking my back sight azimuth and I'm subtracting it from my foresight azimuth to get the interior angle. Now again, 87, 39, 38, that is my final adjusted angle. But when I go back up here to my first adjusted angle was 87, 39, 31. So you have an adjusted angle and a final adjusted angle. And I did the same thing here. 213, so I would have 360, which is 360. You had 360, that would be 573. And of course, you have 573, you do your subtraction, and then you get yourself your 8459.03. And then I did the same thing right here by 9107. And then when I totaled everything out, now something I didn't explain, and now I explain it to you. For my total, this is why I call it my final angle. I took the adjustment from the first adjustment and I either added it or subtracted to get the sum or the difference. Now, let me go back and show you how I got this +7 for my adjusted angle. So my adjusted angle was 87, 39, 31. Now, my final adjusted angle was 87, 39, 38. So how did I get to 87, 39, 38? I had to adjust it by 7 seconds. Now, going back to 5, 96, 13, 57. Well, I had to add a second to my final adjusted angle, and that's where I came down with 9613.51. Now, my first adjusted angle was 8459.11, but my final adjusted angle was 8459.03. So what did I do? I subtracted 8 seconds. Now, sometimes you don't have to do anything. My adjusted angle and my final adjusted angle are equal. 9107.21, 9107.21, and then I go to my column, I add everything up, and it closes. Came to 0. And if you don't come to 0, you did something wrong. But what you just saw was how to use the Bowditch method or the compass method to close a traverse. Again, it's about your accuracy. It's about your equipment. Has your equipment been calibrated? Did you write a number correctly? Did you interchange numbers? Errors take place. And if you're wondering about surveying, nothing is perfect. So we have to do some error corrections. And there's statistics involved with it. There's geometry. There's algebra involved with all these corrections. You even have to understand the sexagesimal system when we use degrees, minutes, and seconds. And just like I did, set everything up in a table and use the formulas, and you will get the information. But you have to understand the data in the field. And this all comes by practicing. And now there are other traverses that are out there that are polygons, and you also have open traverse. Most of us, when we're dealing with property, we deal with closed traverses. So again, let's take a look at all the information that I have provided. Here is part of surveying. Look at this video over and over and over again. If you're taking a course in surveying, you're going to see this in the beginning surveying class. Look at the information that I have provided. Email me. If you need some help, I'll supply it, but all the information is there. And that concludes this video on traverse computation using the Compass-Bowditch method. If you like what I just presented, please comment, share, and subscribe. And if you're looking for some social and political content, check out my main channel, the 411 Talk Zone Radio Show channel on YouTube as well. Now, if you cannot find the 411 Talk Zone Radio Show or the QCIS channels on YouTube, all this information is uploaded onto my Twitter page. Now, for the QCIS channel, I take it one step further since it's an educational channel. You can also find the QCIS channel on my LinkedIn page. And once again, thank you for viewing this content on the QCIS channel. On this channel, get a daily dose of science, technology, engineering, and math. My name is Leon Jones. I want you all to have a wonderful, gracious evening.